Now I will be moving on to take a look at multi-threading. Multi-threading is a multi-processing operating system which can run several processes at the same time. Each process has its own address and memory space. The OS's scheduler decides when each process is executed. Only one process is actually executing at any given time. However, the system appears to be running several programs simultaneously. Separate processes do not have access to each other's memory space. Many OSs have a shared memory system so that processes can share memory space. In a multi-threaded application, there are several points of execution within the same memory space. Each point of execution is called a thread, and threads share access to memory. So why should we use multi-threading? In a single-threaded application, one thread of execution must do everything. If an application has several tasks to perform, those tasks will be performed when the thread can get to them. A single task, which requires a lot of processing, can make the entire application appear to be sluggish or unresponsive. In a multi-threaded application, each task can be performed by a separate thread. If one thread is executing a long process, it does not make the entire application wait for it to finish. What kind of applications use multi-threading? Any kind of application which has distinct tasks which can be performed independently. Any application with a GUI. Threads dedicated to the GUI can delegate the processing of user requests to other threads. The GUI remains responsive to the user even when the user's requests are being processed. Also, any application which requires a synchronous response. Network-based applications are ideally suited to multi-threading. Data can arrive from the network at any time. In a single-threaded system, data is queued until the thread can read the data. In a multi-threaded system, a thread can be dedicated to listening for data on the network port. So how does it all work? Each thread is given its own context. A thread's context includes virtual registers and its own calling stack. The scheduler decides which thread executes at any given time. The VM may use its own scheduler. Since many OSs now directly support multi-threading, the VM may use the system's scheduler for scheduling threads. The scheduler maintains a list of ready threads, the run queue, and a list of threads waiting for input in the wait queue. Each thread has a priority. The scheduler typically schedules between the highest priority threads in the run queue. Let's take a look at thread support in Java. Few programming languages directly support threading, although many do have an add-on thread support. Add-on thread support is often quite cumbersome to some though. The Java virtual machine has its own runtime threads, used for garbage collection. And threads are represented by a thread class. A thread object maintains the state of the thread. It provides control methods such as interrupt, start, sleep, yield, and wait. When an application executes, the main method is executed by a single thread. If the application requires more threads, the application must create them. There are different thread states. These consist of created, running, blocked, and dead. A thread state changes based on control methods, such as we previously mentioned, start, sleep, yield, wait, or even notify. And termination of the run method. As you can see here, we have a diagram showing this process, and the run method terminating, and therefore when that happens, the thread goes into the dead state. So we have created, runnable, blocked, or dead. How does a thread run? The thread class has a run method. Run is executed when the thread start method is invoked. The thread terminates if the run method terminates. To prevent a thread from terminating, the run method must not end. Run methods often have an endless loop in order to prevent the thread termination. One thread starts another by calling its start method. The sequence of events can be confusing to those more familiar with a single-threaded model. When it comes to creating your own threads, the obvious way to create your own threads is to subclass the thread class and then override the run method. This is due to the fact that this is the easiest way to do it, but it is not the recommended way to do it. Because threads are usually associated with a task, the object which provides the run method is usually a subclass of some other class. If it inherits from another class, it cannot inherit from a thread. The solution is provided by an interface called runnable. Runnable defines one method, public void run. One of the thread classes, constructor, takes a reference to a runnable object. Let's look at using runnable. In the example below, when the thread object is instantiated, it is passed a reference to a runnable object. The runnable object must implement a method called run after this is passed to the runnable object. When the third object receives a start message, it checks to see if it has a reference to a runnable object. If it does, it runs the run method of that object, or if it does not, it runs its own run method. Here is some example code. When it comes to properly terminating threads, the thread class had a stop method in Java 1.1. One thread could terminate another by invoking its stop method. However, using stop could lead to deadlocks, and due to that fact, the stop method is now deprecated, and it is recommended that you do not use the stop method to terminate a thread. The correct way to stop a thread is to have the run method terminate. To do this, we add a Boolean variable which indicates whether the thread should continue or not. Here's an example of some code. Again, as always, be sure to write these out if you want to and practice them, just so you can see what happens when you do happen to code them. Let's take a look at creating multiple threads. The previous example illustrates a runnable class which creates its own thread when the start method is invoked. If one wished to create multiple threads, one could simply create multiple instances of the runnable class and send each object a start message. Each instance would then create its own thread object. But is there a maximum number of threads which can be created? The answer to this is no. There is actually no defined maximum in Java. If the VM is delegating threads to the OS, then this is platform dependent. But a good rule of thumb for a maximum thread count is to allow 2 megabytes of RAM for each thread. Like everything, there exist thread priorities, and every thread is assigned a priority between 1 and 10. The default is 5. The higher the number, the higher the priority. This can be set with a set property int a priority piece of code. The standard mode of operation is that the scheduler executes threads with higher priorities first. This simple scheduling algorithm can cause problems. Specifically, one high priority thread can become a CPU hog. A thread using vast amounts of CPU can share CPU time with other threads by invoking the yield method on itself. Most OSs do not employ a scheduling algorithm as simple as this one. Most modern OSs have thread aging. The more CPU a thread receives, the lower its priority becomes. The more a thread waits for the CPU, the higher its priority becomes. Because of thread aging, the effect of setting a thread's priority is dependent on the platform. We have yield and sleep. Sometimes a thread can determine that it has nothing to do, and sometimes the system can determine this, for example, waiting for the I/O. When a thread has nothing to do, it should not use the CPU. This is called a busy wait. Threads in busy wait are busy using up the CPU doing nothing. Often, threads in busy wait are continually checking a flag to see if there is anything to do. It is worthwhile to run a CPU monitor program on your desktop. You can see that a thread is in busy wait when the CPU monitor goes up, usually to 100%, but the application doesn't seem to be doing anything. Threads in busy wait should be moved from the run queue to the wait queue so that they do not hog the CPU. We can use yield or sleep time. Yield simply tells the scheduler to schedule another thread. We're going to stop here and continue with multi-threading in the next lecture. I'll see you guys there, where we will pick up from this exact spot.